Now, this idea of electromagnetic induction, that's more or less how power plants work. Suppose we had some steam and we drove a turbine, then that has some mechanical input. You have a big heavy magnet in there, you have a coil of wires inside of that magnet, you move the coil of wires and boom, you have voltage. Now, a long time ago, some fellows by the name of Nikola Tesla and George Westinghouse showed that we could actually generate enough power to light up cities, and that's kind of a good thing. But we do need to perhaps transform those voltages into something that's more palatable for like our electric grid or something like that. And that's going to lead to this idea of a transformer. And what the transformer is going to do is going to transfer voltage from part number 1 to part number 2. But you notice that there's not a physical connection between circuit number 1 and circuit number 2. So we're transforming voltage. We are not actually making a physical connection. So kind of what we have is we have an input coil of wires, and that's powered by some AC source, or maybe a generator or something like this. And what we're doing is we have an output. What we're actually doing is we're taking our voltage and we're sloshing it up and down, or we're sloshing it back and forth and back and forth and back and forth. That's generating a magnetic field inside of this guy right here. Now that magnetic field is going back and forth, back and forth, back and forth. This secondary circuit, well, it doesn't like that change, and so what it does is it starts to generate something to oppose it, and it's going to go back and forth, back and forth, back and forth in exact opposition. So what we've essentially done is we've transformed a voltage from side number 1 into side number 2 just by the fact that nature doesn't like a change. Now we have a special name for this. It's called a transformer. And what it does is it transfers power from one circuit to the other. It does need to be alternating current. It cannot be direct current, because if it was direct current, then the current and hence the magnetic field on this side over here would be a constant. If it was a constant, then there's nothing for nature to oppose. So it only works with alternating current, and that's why Nikola Tesla and George Westinghouse won the battle of the power grid. And that's why all of our circuitry is going to be AC. Note that it does not transfer charge between the circuits, and it only transfers power. Something else is the power on the secondary has got to be the same as the power on the primary, because this thing doesn't generate power, it just transfers power. And you can kind of notice that if we had 120 volts of AC over here, and we had 8 coils of wire, then if we had 8 coils of wire over here, we would have 120 volts. Now, it does help to have the iron core to get some of those magnetic domains lining up as it goes back and forth. But we can't mess around with the power, but if we start to mess around with the number of turns, we can start to mess around with the voltage. And it turns out that transformers can actually step up voltage or step down voltage. A step-up transformer is going to have a higher voltage in the secondary than the primary. The secondary is also going to have more turns. More turns means more voltage. Step down is going to be the exact opposite. It's going to have a smaller voltage in the secondary than the primary, and it's going to have less turns. Less turns means less voltage. Now, there's a really important relationship for transformers, and essentially what we're going to have is we're going to have the voltage in the primary divided by the number of turns in the primary, and that's going to be equal to the voltage in the secondary divided by the number of turns in the secondary. So let's get a little bit of practice using this guy. Suppose I had 120 volts over here and I had 3 turns. Then if I were to have a transformer with 300 turns over here, it's got more turns, so it's going to be a step-up transformer. And what we could do is we could say the voltage in the primary divided by the number of turns in the primary should be equal to the voltage in the secondary divided by the number of turns in the secondary. And what we would kind of say is we're going to have our 120 volts divided by 3 turns. That's going to be 40. This one over here would inherently have a voltage of 12,000 volts. That's dictated by the number of turns, and a 12,000 divided by 300 is going to give you the same number. It's going to give you 40. So the voltage in the secondary must be higher. Again, this is a step-up transformer. Step-down transformer is going to have fewer turns. If we had 120 volts and 30 turns, well, we're going to say the voltage in the primary divided by the number of turns in the primary. That's got to be equal to the voltage in the secondary divided by the number of turns in the secondary. Here I have 120 volts, and I have my 30 turns. That's going to be 4. The secondary might power something really small, like a halogen bulb or your cell phone or something like that. That would have a voltage of 12. Again, that 12 would be dictated by the number of turns, and 12 divided by 3 would be the same number. It would be 4. The voltage in the secondary would always be lower. So let's come back to this FET simulation that I've been messing around with. This is an electromagnet. Here we have a coil of wires, and I know that if I move this thing in there that I'm going to get some voltage. I've already shown you kind of that. But now let me not use a DC power source. Let me use an AC power source, and you can kind of see how this guy is now sloshing back and forth, back and forth, back and forth. Well, this guy over here is going to slosh back and forth kind of in response to that. And so what we're doing is we're transforming power from circuit 1 to circuit 2. We're not transforming the charge. We're just getting power from one to the other. And the magnetic field is going to flip back and forth, back and forth, back and forth. Just a quick little check your neighbor. A step-up transformer in a circuit can step up voltage. It cannot step up energy. We can mess around with the number of coils and mess around with the voltage, but we can't actually mess around with the energy. Or we can't increase or decrease the energy. So it's going to transfer the energy. In a perfect one, it would be 100%. Now, something that we know is the power in the primary has got to be equal to the power in the secondary. And if you remember a couple of chapters ago, I did have a relationship between power, current, and voltage. So what we could say is the power has got to be the same, power primary, power secondary. We could also say that the product of the current and the voltage in the primary has also got to be equal to the product of the current and voltage in the secondary. So let's just really quick take this concept and come back to my step-up transformer. This one, I went from 120 volts up to 12,000 volts. My voltage went up by a factor of 100. Therefore, my current had to go down by a factor of 100. The reason for that is because the product of the power and the current has got to be equal to the power and the current. For this one, I stepped it down from 120 volts down to 12 volts. Again, power times current has to be power times current, so my current would have to go up by a factor of 10 to make that product a constant. So let's just talk about some applications of this. Let's talk about power production and power transfer. Something that we know is high current is actually quite wasteful. It heats the wires up. High voltage is not so wasteful. So what we do is after leaving the power station, we step up the voltage, and then we start to get near the power grid, and high current's actually kind of dangerous, or high voltage is kind of dangerous. So we get to the cables near your house, and we're actually going to step that voltage down, and it probably step down again before it goes into your house. Where is it stepped down at? Well, if you live in the country, you see these guys right there, they hum, and when they go off, they make a horrific noise. That's a transformer, and what it does is it transforms the voltage from something higher to something lower before it enters your house. In the cities and in the suburbs, those are those little green boxes that kind of hum. So all of the energy today is transmitted at high voltage because high current is very, very wasteful. The wires heat up. High voltage is kind of dangerous, but far less wasteful. So kind of what we do is we generate power around 25,000 volts. And so then what we would do is we would take that voltage and we would step it up to a little bit less than a million or so. So right here we would have 1,000,000 volts. Then it gets stepped down again, probably 440 or 240 to 120 inside of your house. Actually, your house probably gets 240 for most of the stuff. Some of the higher voltage appliances, like your dryer, they probably run on 240. Again, the way that we do that is using transformers, a combination of step-up transformers and step-down transformers. Now, before I finish off this chapter, I want to dive into the next chapter just a little bit. And I want to come back to this slide because, it is kind of important. A changing magnetic field is going to cause an electric field. The electric field is going to cause a current, and the current causes a magnetic field. Now, what's going to essentially happen is this changing magnetic field causes a changing electric field causes a changing magnetic field, and we're going to have this self-feeding beast. It says, electromagnetic induction is kind of a two-way street. As long as everything is changing, then we're always going to have induction. Now, when it comes to light is actually going to be an electromagnetic wave. So we've talked about waves, we've talked about electricity, we've talked about magnetism, and we've talked about how they can kind of feed off each other. Now, if I were to have something like a radio tower, and if I were to have an electron, and if I were to slosh that electron up and down at just the right speed, then what's going to happen is I'm going to have this electric field that's going to track my electron, and it's going to go up and down, up and down, up and down. Well, changing electric field means a changing magnetic field, and that is exactly what an electromagnetic wave is going to be. It's going to actually emanate at the speed of light, which is really quite fast. It's 3 times 10 to the 8th meters per second. And what it's going to kind of look like is we're going to have this electric field that goes up and down, up and down, up and down, tracking the electron. We're going to have this magnetic field that changes in response to the electric field. But the changing magnetic field is going to cause a changing electric field. So we're going to have this kind of self-feeding wave that's going to propagate away from the source, probably in some direction that's perpendicular to the two of them. The nice thing about electromagnetic waves is everything that we learned in the first couple of chapters is going to apply. We've talked about something called the wavelength, where the wavelength was 1 full up and 1 full down, and we could be talking about just the electric field here. Well, the wavelength for a mechanical wave is going to look just like the wavelength of an electromagnetic wave. Only electromagnetic waves have a much smaller wavelength. It's going to emanate at a speed. That speed is very fast, 3 times 10 to the 8th. One difference between electromagnetic waves and the mechanical waves we talked about previously is we don't need a medium. Mechanical waves needed some particles to do the wiggling, but in this case right here, what's wiggling is going to be the electric field and the magnetic field. So electromagnetic waves can go through outer space. Outer space is a vacuum. There's virtually no particles there. Mechanical waves cannot. Sound waves cannot. Something that's really nice is we have our old friend from several chapters. We said speed was equal to wavelength times frequency, and that worked for mechanical waves. That can apply to electromagnetic waves as well. So you're definitely going to see this again. The speed that it propagates is always going to be 3 times 10 to the 8th, at least on Earth's surface and in a vacuum.